everyone. Oh, I guess I should scroll up here to the title of today's video. It's been a long time since I've uploaded to this channel. This video is mostly for my current complex analysis students. I wanted to go through just some of the big theorems from section 57. This will be particularly useful for this week's homework. Otherwise, if you're not currently in one of my classes, I hope this can still be helpful. So section 57 deals with consequences of the extension, and by extension we mean the extension of the Cauchy Integral Formula. So just as a reminder of what that is, we say if f is analytic in and on a simple closed contour C, so by simple we mean maybe something like a circle, just without self-intersection, so something like this figure 8 wouldn't be allowed. Closed, meaning it's joined end to end. Again, keep in mind the example of a circle, and taken in the positive sense. By positive, we mean counterclockwise direction. If z naught is interior to C, then the nth derivative of f at z naught is n factorial divided by 2 pi I times the contour integral of f of z dz over z minus z naught to the n plus 1. So we saw in discussion a number of ways that this integration formula is really helpful, and today we're going to go over a couple of theorems that we can get as a consequence of this formula. So the first theorem is if a function f is analytic at a point, then its derivatives of all orders are analytic there too. So this is a really amazing result. If you think about it, we're saying if you know f is analytic at a single point, that's enough to guarantee that all of its derivatives are analytic as well. So let's actually prove it. So this is a good review for what it means for a function to be analytic at a point. So let's recall. So since f of z is analytic at the point, let's say z naught. Remember, this means there exists some epsilon such that f of z is analytic in z minus z naught less than epsilon. So this is the circle centered at z naught of radius less than epsilon, or kind of that disk. So what this means is I have a point z naught. Analytic at this point means I can find some epsilon neighborhood of it so that the derivative of f exists at every point in this neighborhood. And I apologize for the cat noises. I have 5 cats and they are all playing together right now. Come on, guys. Now's not the time. All right, moving on. So we know f of z is analytic in z minus z naught less than epsilon. In particular, we can consider the circle C of radius epsilon over 2 centered at z naught. So let's think about this picture here. We have z naught, we have epsilon, we know f is analytic at every point in this disk. And what we can do next is we can draw a little epsilon over 2 neighborhood. Around z naught, it's going to stay within our original neighborhood, so the derivative of f still exists at every point within this disk that I have shaded. So maybe I shouldn't shade it, but yes, okay. So f of z is analytic in and on C. So this should remind you of the extension of the Cauchy Integral Formula. Remember, we require f to be analytic in and on a simple closed contour C. In this case, C is just a contour, so it's definitely simple and closed, and we have f of z is analytic there. So what we were able to do is, in a previous section of the book, we were able to prove that the second derivative of f of z is equal to Yes, 1 over pi I integral over c f of s ds divided by s minus z cubed. And this is for all z in C. So what this means is we basically proved that this integral exists and it's equal to the second derivative of f. So the existence of this integral gives the existence of f prime for all z in C. So in particular, we've shown that f prime exists in a neighborhood of z naught, or the derivative of f prime. But remember, this was equivalent to f prime being analytic at z naught. So therefore, f prime is analytic at z naught. And repeating this argument, for higher derivatives, gives the result. All right, so that's theorem 1. So if you're one of my students for this week's homework, I'm not sure, I don't think this theorem really is going to show up too much, but it's a really important one and something to keep in mind. Next theorem, theorem 3. So I did skip theorem 2 just for the sake of time in this video, but theorem 3 is very, very useful and it does show up a lot on your homework, so let's go over it. Theorem 3, this is also called the Cauchy Estimate. So let me kind of write it here. And what it says is, suppose a function f is analytic inside and on a positively oriented circle CR centered at z0 and with radius r. If mr denotes the maximum value of the modulus of f of z on CR, then we have this nice bound for the nth derivative of f at z0 and modulus. So it's bounded above by n factorial times mr, so that maximum value, over Rn. So it might look a little bit strange right now, but it actually follows quite nicely from the Cauchy Integral Formula. So let's actually go through the proof. So I'm going to say recall. So remember, we have f as analytic inside and on a positively oriented circle CR centered at z0. So by the extension, we know that fn of z0, this is equal to n factorial over 2 pi I integral over CR f of z divided by z minus z0 to the n plus 1 dz. And we're also going to use the basic estimate here, so this is a good reminder of how we can bound the modulus of a contour integral. So let's start bounding things. So let's look at modulus of nth derivative of f at z0. This is going to be equal to the modulus, so I'm going to use modulus rules. I can split along multiplication, so modulus of n factorial over 2 pi I in modulus times the modulus of the integral over CR f of z divided by z minus z0 to the n plus 1 dz. Now remember, we can bound this contour integral by taking the maximum value of the integrand along CR and multiplying by the length of CR. If we try to maximize this without parametrizing first, it's a little bit tough. So what we're going to do is I'm going to parameterize CR by, and remember, CR is centered at Z0, and it has a radius of capital R. It's a circle. So this is going to be Z0 plus capital R e to the IT for t living in between 0 and 2 pi. So then if I parameterize this integral, what I get is integral from 0 to 2 pi f of gamma of t divided by, and so z is gamma of t, so this is z0 plus r e to the it minus z0. We're left with the quantity r e to the it to the n plus 1. I can't forget to multiply by gamma prime of t, so this is ri e to the it dt, all in modulus. Well, I guess I've just written the parameterization, so then let's take modulus on the outside. Cool. All right, so moving along, I'm going to keep this, so we have n factorial over 2 pi I in modulus. N factorial is a positive number. It's n factorial over modulus of 2 pi I. You can think of that as modulus of 2 pi times modulus of I, so it's just 2 pi. And now let's work on actually bounding this integral. So right now I have integral from 0 to 2 pi. This is f of gamma of t divided by r to the n plus 1 e to the it times n plus 1 times ri e to the it dt. I'm not going to worry about simplifying right now because when we take the modulus, these e to the it's are actually, they have modulus 1, so those are going to go away. So now let's actually use our inequality. So let's pass the absolute value, or sorry, the modulus inside the integral. So this is less than or equal to n factorial over 2 pi, integral from 0 to 2 pi. This is modulus of f of gamma of t divided by r to the n plus 1. Remember, r is greater than 0, it's a radius. If I take modulus of e to the it n plus 1, that's just 1. If you need a refresher on why that's true, apply Euler's identity, and you're going to use the fact that cosine squared theta plus sine squared theta is 1. And same argument for e to the it living over here. Modulus of I is 1, so what we're left with is modulus of r, but that's a positive number, so it's just r dt. So all I've done right now is just pass the modulus inside of the integral at the cost of a less than or equal to. We can always do that. And now let's apply the basic estimate. So to estimate this contour integral, I'm going to multiply by the length of the contour times the maximum value of the integrand. So this is less than or equal to n factorial over 2 pi times, so 0 to 2 pi, that has a length of 2 pi. R to the n plus 1 and r, these are constants, so I don't need to worry about maximization. So I'm going to, if I have r over r to the n plus 1, in the denominator I have an r. And then we have modulus f at gamma of t, so this is just bounded by the maximum value mr. So this is the maximum value that f takes on the contour. Maximum value f takes on CR. And if we do some cancellation, so 2 pi and 2 pi goes away, and what we're left with is n factorial mr over capital R. Oops, and sorry, there was a mistake here. This is r to the n. And if we recall our original statement, so we needed to show that f nth derivative as z0 in modulus is bounded above by n factorial mr over r to the n, and that's exactly what we have shown. So that completes the proof. All right, everyone, I'm going to end the video here. I'll probably make a video soon with lots of examples. My apologies for the cat noises earlier, and I'll see you in the next video. Thank you.